After our extensive discussion of the Fermi gas, I'd now like to turn our attention to Bose gases and consider a number of special cases. And the first example of a Bose gas that I'd like to discuss is a gas of photons. And this will later allow us to describe phenomena such as black body radiation. And to start with, we should say a few words about photons in general. Photons are elements of the quantized electromagnetic field. So when you take the classical electromagnetic field and you quantize it, then this gives rise to a new kind of elementary particle, which is the photon. Photons are massless. They move obviously like electromagnetic waves. They move with the velocity of light. And the energy of a photon is related to its momentum by a constant of proportionality. The energy is proportional to momentum. And the relationship between energy and momentum is called the dispersion relation. And it's very simple for a photon. The energy of a photon that has momentum p equals the velocity of light times the momentum. And photons are bosons. There's a general and very deep result in quantum field theory that relates the spin of elementary particles with their statistics. It's called the spin statistics theorem. It says that elementary particles that have half integer spin are fermions, and elementary particles that have integer spin are bosons. The electron has spin 1/2, and therefore it's a fermion. Now the photon is a spin 1 particle, and therefore it is a boson. A photon has two possible polarizations. It has two possible orientations of its spin. In the case of a massless particle, strictly speaking, one doesn't talk about spin, but one talks about helicity. It corresponds classically to two different polarizations. So each momentum state of the photon has degeneracy 2 in the sense that there are two possible polarizations of the photon. So you can have a photon with a given momentum with either of the two polarizations. So the momentum state has degeneracy 2. And for this degeneracy, we use the letter little g. So there are two polarizations, and g is the degeneracy factor. And you remember when we want to describe a perfect gas, no matter whether it's quantum or classical, what we will always need is the level density. So we look at a single particle in the gas, a single constituent of the gas, and we ask, what is the density of states for this single particle in the gas? The level density arose, this concept arose when we made the transition from discrete levels to a continuum, which we can do when we have a large volume. We are in the continuum limit. And then we saw already, we looked at that for non-relativistic particles in 3 dimensions. We found a result for the level density of non-relativistic massive particles in 3 dimensions. And the summation over discrete levels is then replaced by an integral in momentum space. And the general result that we found for non-relativistic particles still holds for relativistic particles. So this is independent of whether they are relativistic or non-relativistic. And that is that you have to integrate over three-dimensional momentum space. You have the spatial volume, and you have to divide by Planck's constant cubed. Now this is not h bar, but it's simply dh, the original Planck's constant. So the result that we found for non-relativistic particles, we derived that at the time by looking at a potential well with infinitely steep walls, and from that we derived the density of states for the non-relativistic particles. You can also write that always in this form, that you say the number of quantum states in a given classical phase space volume is that phase space volume divided by Planck's constant cubed. And this still holds, this carries over to the relativistic case, this still holds here also for photons. If you wish, you can rederive that also starting again from a potential, sort of from a closed box, and you look at all the possible modes of photons inside this box, and you will again arrive at this general formula for the integration over states. Now, what we have to take into account here is this degeneracy, the fact that each momentum state comes in two versions corresponding to the two possible polarizations. So when we count the number of states, when we sum or we integrate over all possible states of a photon, we have to account for this degeneracy, and we do that by simply multiplying with the degeneracy factor G. So in this case, there's just a factor of 2, and this reflects the fact that each photon comes in two possible polarizations. As we did in the non-relativistic case, we can go to spherical coordinates in momentum space, and we can write this as follows. The degeneracy factor is 2. I'd like to use h bar instead of h, so this gives us an extra 2 pi cubed, and then we have h bar cubed. And then finally the integration over in momentum space, we have an integration over angles, but just as in the previous non-relativistic case that we had considered, given that the energies don't depend on orientation, they just depend on the magnitude of momentum, we can perform immediately the integration over angles. This just gives us a factor of 4 pi, and we are left with an integration over the magnitude of momentum, dp, and then we get a p squared from the use of spherical coordinates. At this point, we can use the simple dispersion relation for photons and simply replace the magnitude of the momentum by energy divided by velocity of light. So we get a prefactor, volume over the pi's partially cancel out, we are left with the pi squared, the numbers cancel out, then we have an h bar cubed, and we have a velocity of light cubed, and we have an integral the epsilon squared. Now in our general discussion we said when we go to the continuum limit, we replace the sum over energy levels, the sum over I, we replace that by an integral over all possible energies in our continuum, d epsilon times the level density, this curly d of epsilon. And here we can simply identify this factor here with the level density. So the level density for photons goes like epsilon squared. When you compare that to the non-relativistic case, there the level density went like the square root of epsilon. So that's quite a different behavior. When we integrate that over epsilon, then we get the number of states up to epsilon, this curly n, the number of states up to epsilon. Now the integral of epsilon squared, this gives a 1/3 epsilon cubed, and the remaining factors just stay unchanged, so we have a v over pi squared h bar cubed velocity of light cubed. This is the number of energy levels, the number of states of a single photon up to energy epsilon. So when you compare it to the non-relativistic case that we had looked at earlier, there are two key differences here. One is that we use the relativistic dispersion relation, and this gives us a different dependency of the level of the level density on epsilon. And we took into account the degeneracy factor, the factor 2, that comes from the two possible polarizations. Next we can turn to the partition function. As always, when we want to understand the thermodynamic properties of a new substance, this is always the starting point. You always start with calculating the partition function, and once you have that, then you can derive from that everything you want. The first question to ask here is which partition function we should use. We have the choice between microcanonical, canonical, grand canonical. The question is which of these we should use. What's different here compared to the gases that we have looked at so far is that the number of photons is not a constant of the motion. It's not a conserved quantity. When we have electrons or neutrons in a neutron star or we have hydrogen atoms in a gas, of course the number of these particles is conserved. But the number of photons is not conserved. It's not a constant of the motion. And when we describe a gas of photons, so we have a box and inside there's quantized electromagnetic radiation, then what we are given is, say, the temperature of this gas or the energy of this gas, but we are not given the number of photons. The number of photons is not part of the macroscopic data that we are given. It's not given as a sharp value, and it's not even given as an expectation value. When we look at a black box filled with electromagnetic radiation, all we are given typically is as I said, is the energy or the temperature or the volume, but we are not given the number of photons. As a consequence, the partition function should not depend on the number of photons. The partition function should only depend on macroscopic data that is given to us, which is either the energy and the volume, or the temperature and the volume, and nothing else. So the choice is really reduced to either the microcanonical ensemble, in which case we would be given the energy and the volume, or the canonical ensemble, in which case we are given the temperature and the volume. But the grand canonical ensemble is not really a choice that is open to us, because the particle number simply doesn't enter in the macroscopic data that we are given. Let me write this down just in a few words. So we are not looking at photon number, we are we don't have an associated Lagrange parameter alpha or mu. All that is given to us is the energy or the temperature and also the volume. So this means that we should work either with the microcanonical or with the canonical partition function. We know that they are, in terms of the thermodynamic properties that you can derive from them, they are equivalent. We studied that in general. So it's up to us. We can choose the more convenient partition function, and the more convenient partition function here is the canonical partition function. So here we shall use the canonical partition function. What's the formula for the canonical partition function? The log of the canonical partition function as a function of beta and volume. So no n in here, just beta and volume. It's the same formula as the one that we have for the grand canonical partition function. So it's again has this form beta times the integral over all energies, and the energies start at 0, go up to infinity, number of states up to epsilon, times occupation factor, where here we should use the occupation factor for bosons, and without the chemical potential. You obtain the grand canonical partition function in the same way in which you obtain the grand canonical partition function, only that in the canonical case, there is in the exponent no alpha n, which means that you set the alpha simply equal to 0. And so you have the same formula, only that alpha and mu are equal to 0. So what's the occupation factor for bosons with 0 chemical potential? It's 1 over e to the beta epsilon, and then there's no mu there, minus 1. That's the occupation factor for bosons. The curly n we had calculated on the preceding page. That goes like epsilon cubed, some prefactor times epsilon cubed. And then in order to evaluate this integral, we can substitute x as beta times epsilon, and then you find with all the prefactors, you find this is volume divided by 3 pi squared h bar cubed velocity of light cubed. That's the factor that appears in the number of states, the n of epsilon. Then from the substitution, you get a kt cubed, and then you have an integral from 0 to infinity dx x cubed divided by e to the x minus 1. Now this integral is a special integral, and it has the value pi to the power 4 divided by 15. And then you find that this is pi squared divided by 45 and then h bar c cubed times the volume times kt to the power 3. This is the log of the canonical partition function of a photon gas. This is the starting point, and we can now start to derive some properties, thermodynamic properties of the photon gas. In particular, we can look at the internal energy, the entropy, and the pressure of a photon gas. Let's start with the internal energy. The internal energy according to our general rules, can be obtained from the log of the partition function by taking minus the partial with respect to beta. Now the log of the partition function goes like temperature cubed, or if expressed in terms of beta, it goes like beta to the minus 3. When we take the partial with respect to beta, we expect that it goes like beta to the minus 4. And indeed, when you take into account all the prefactors or the numerical factors, you find it's pi squared over 15 h bar c cubed times volume times kT to the power 4. So in particular, this goes like temperature to the power 4. That's very different from the classical gas, where we had a behavior, internal energy was proportional to temperature. Here it goes like temperature to the power 4. We can look at the entropy, well, divided by Boltzmann constant. According to our general formula, this is the log of the partition function plus beta times u. The log of the partition function goes like temperature cubed. U goes like temperature to the power 4, but then we multiply with beta, which is 1 over kT, so the product also goes like temperature cubed. So we expect that the entropy goes like temperature cubed. When you take into account all the prefactors, you find the result 4 pi squared divided by 45 h bar c cubed times volume times kT to the power 3. So indeed goes like temperature cubed. In particular, this implies that as the temperature goes to 0, the entropy per unit volume, that goes like temperature cubed, and therefore also goes to 0. This is a kind of behavior that we've seen several times already, also in some of the problem sets that you have worked on, that as the temperature goes to 0, the entropy divided by volume, or sometimes entropy divided by particle number, also goes to 0. That's a quite universal behavior. This is the so-called third law of thermodynamics. We'll come back to that very soon when we talk about the laws of thermodynamics, but here you already have another instance of it. Then finally, let's look at the pressure. The pressure, according to our general recipe, is 1 over beta times the partial with respect to volume of the log of the partition function. The log of the partition function is simply proportional to volume, so taking the partial with respect to volume simply amounts to dividing by volume, and we get all the remaining factors in the log of the partition function. The log of the partition function, once again, it goes like temperature cubed. Here we divide by beta, which is the same as multiplying with kT. So we expect that the pressure goes like temperature to the power 4. And with all the prefactors, you find this is pi squared divided by 45 h bar c cubed kT to the power 4. When you relate that to the internal energy that we have found above, that also went like temperature to the power 4, you see that the internal energy equals 3 times pressure times volume. You can compare this to a non-relativistic gas. There we found that the internal energy is 3/2 times pressure times volume. You had on one of the recent problem sets, one of the exercises was to derive a very general formula for the internal energy and the relationship to pressure times volume. There's a general formula that says that the internal energy is equal to the spatial dimension divided by the power of momentum in the dispersion relation, when you relate energy to momentum. Now, non-relativistically, you have kinetic energy is p squared over 2m, so the power of p that appears in this dispersion relation is 2. And for this reason, you have in the non-relativistic case, you have the prefactor 3/2. You have spatial dimension 3 divided by this power of momentum, which was 2. In the relativistic case, you have the dispersion relation epsilon is proportional to p, so p momentum to the power 1. And therefore you have the prefactor in front of the PV, you have spatial dimension 3 divided by the power of the momentum in the dispersion relation, which is 1. So this gives a prefactor 3. This is where this comes from, and this is what you derived on your problem set. And here we have it confirmed in this special instance of the photon gas. Now we come to the Planck distribution, which is also of historical interest, because this is the first instance where Planck's constant appears. So historically, the Planck distribution is the first formula derived by Planck in which this new constant of nature appeared. So it's closely linked to the birth of quantum mechanics. What does the Planck distribution describe? It describes the energy density of photons. So in modern language, it's the energy density of photons. Density meaning energy per volume, per unit volume, of photons whose frequency lies in a certain range, certain infinitesimal range. So we have photons whose frequencies are in the infinitesimal range between nu and nu plus d nu. So we consider only photons whose frequencies lie in this infinitesimal range, and these photons together, they have a certain energy, and then we divide by the volume, and that's the energy density of those photons whose frequencies lie in this interval between nu and nu plus d nu. How do we calculate this energy density? Density means, first of all, that we divide by volume, so we have a factor 1 over volume. Then what we should do is we should consider the number of photons in this frequency range and multiply with their energy. And then we have the total energy of these photons in this frequency range. How do we obtain the number of photons whose frequency lies in this interval? Well, the number of photons with frequencies in this interval, or the way we can calculate that, is that we consider the number of states in this interval and multiply the number of states with the occupation of these states. So with the occupation factor, which gives us the fraction of states that are occupied. When I multiply the number of states with the fraction of states that are occupied, then I get the number of photons in this range. So we should multiply this with the occupation factor. Now, together this gives us the number of photons with frequencies in the given interval. And now to obtain the energy that these photons have, we have to multiply the number of photons with the energy of each photon. And the energy of a photon in this range, given that this range is infinitesimal, we can assume for all photons the same energy, namely Planck's constant h times frequency nu. That's the photon of a single, that's the energy of a single photon in this range. Now, what about the previous factors? The number of states in this interval, that's the density of states at this energy. Now, the energy is Planck's constant times frequency nu. So it's the density of states at h times nu times the width of this interval. The infinitesimal width of this interval, so d epsilon, and the energy once again is h times nu. So the number of states is the density of states as a function of energy times the energy and interval, and we replace the energy by h times nu for photons. And the occupation factor, this is our factor f of epsilon, and again I replace the energy by h times nu. So this is the formula for the energy density of frequencies of photons in this frequency range. For all these quantities we have formulas. We have a formula for the level density. We have the occupation factor, that's for bosons, that's 1 over e to the beta epsilon minus 1. So this will give rise to e to the beta, which is divided by kT, times epsilon, and the energy epsilon, this is once again Planck's constant times frequency nu, minus 1. This is the occupation factor. I said from the density of states, we expect a nu cubed. Then we have the width of the frequency interval. This gives us a d nu. And then we have all the other prefactors, and together they give 8 pi Planck's constant h divided by velocity of light cubed. When you draw this energy density as a function of nu, of the frequency nu, then you find a curve roughly like this, and this is a quantum result. Before Planck, certain limiting cases were known that could be calculated with the help of classical theory. There was a formula describing the low frequency limit, the so-called Rayleigh formula, and this formula gave a curve like this. So this is for the low frequency limit. And then there was also, before Planck, there was a classical formula known for the high frequency limit. This was Wien's formula that looked approximately like that. This was the Wien formula for the high frequency limit. These two are classical results, and one of the problems at Planck's time was that these two formulas apparently didn't match. They were in contradiction to each other, and there was no possibility to connect these two formulas. And the story goes that initially Planck devised his formula as an interpolation formula between these two limiting results. And this was the first instance where this new constant h appeared. And then, of course, this was the starting point of a long story ending in quantum theory. So this is of a lot of interest, both physically but also historically, because indeed this was historically the first instance when Planck's constant appeared. Let us next look at blackbody radiation. The idea is the following. You have a large box. Inside this box, you have electromagnetic radiation. You quantize it, and you have a photon gas. And the photon gas is described by the partition function that we had derived before. On one of the sides of the box, there is a little hole with area A. Out of this hole, photons can be emitted. So there are photons coming out of this little hole. Now you wonder how much energy in the form of quantized electromagnetic radiation, how much energy leaves this hole per unit time. How much energy is emitted, how much radiation energy is emitted by this black body through this hole per unit time. So let me indicate here a little clock. There's a time interval delta t. And the question is how much energy leaves the hole or is emitted through the hole in the time interval in delta t. In order to answer this question, you have to think about how many photons leave the hole, how much energy they carry with them. And one very first consideration that you can make is a purely kinematic argument. You know that all photons travel at the speed of light. When I have a time interval delta t available in which photons can leave the hole, then certainly no photon can kinematically reach the hole if it's further away from the hole than velocity of light times delta t. If it's further away from the hole than c times delta t, it cannot possibly even reach the hole in this time interval delta t. So what we can do is we can draw around this hole, we can draw a half sphere. This half sphere has a radius c times delta t. And only photons inside this half sphere can potentially reach the hole and exit through the hole. But of course, not all the photons inside this half sphere will exit. Only some of them, only a fraction of them. Only those that travel just in the right direction so that they hit the hole and then can pass through it. So next we should consider which fraction of the photons actually do exit and pass through this hole. So to do that, let us look at this hole here through a magnifying glass. Okay? So let's magnify the neighborhood of the hole. Here I would like to draw it just without perspective. This is the wall of the box. And here we have the hole. Let me indicate an axis perpendicular to the wall. So this is perpendicular to the wall. And here this is the hole, which we said has area A. Now let's consider inside this half sphere, so we're talking about the photons that potentially can exit. Inside this half sphere, let's pick an infinitesimal volume element, dV. And inside this small volume element, let's say there happens to be a photon or several photons. Now, viewed from this infinitesimal volume element, the whole actually does not have area A. But viewed from this volume element, the whole has an effective area or a visible area, which is the actual area A times the cosine of this angle theta. So the visible area is the actual area times the cosine of the angle theta. That's the visible area as viewed from this infinitesimal volume element. Let's say that this infinitesimal volume element is a distance r away from the whole, where the distance is at most c times delta t. So we are within the half sphere. Now, if we also introduce an angle around this axis that I indicated, this axis here, and the angle around this axis we call phi, then we can use r, theta, and phi as spherical coordinates to describe the location of this volume element. Now, from the photons inside this small volume element dV, which fraction will exit through the hole? Only those photons whose momenta have a direction inside this cone that I indicated in purple. Yeah? All the photons whose momenta point in a direction that's inside this purple cone, those photons will exit, and all the other photons will hit the wall and be either absorbed or reflected, but they will not exit. So what is the fraction of photons exiting? If we assume that the directions of the photons, photon momenta, are uniformly distributed, so the system is isotropic and all directions of the momentum are equally probable, then the fraction of photons exiting equals the fraction of the spatial angle of this purple cone divided by 4 pi, which is the full spatial angle corresponding to all possible directions. Now, what is the spatial angle of this purple cone? That is the visible area, A times the cosine of theta, divided by distance squared. That's the spatial angle of the purple cone, divided by 4 pi, which is the full spatial angle of all possible directions. So this is assuming isotropy, assuming that all directions of photon momentum are equally likely. Yeah, so this is of the photons in this infinitesimal volume, dV. This is the fraction that will exit through the hole. Now this is a formula for the fraction of photons exiting, of photons in this infinitesimal volume. In the next step, what we should look at is the fraction of photons exiting, the fraction of all the photons inside this half sphere, this gray half sphere that contains all photons that can potentially exit. And we can wonder which fraction of those photons actually leave the box. This is our next question. So we consider now the half sphere and no longer just an infinitesimal volume element. And we ask within the half sphere, what is the fraction of photons that are emitted, that are leaving through the hole? In order to calculate that, we should look at the result from the previous page. So the fraction of photons emitted from such an infinitesimal volume element. This fraction was the area of the hole times cosine theta divided by 4 pi r squared. This is the result from the previous page. And now we should integrate over volume, namely over the volume of the entire half sphere. And we do that in spherical coordinates, in the spherical coordinates that we had introduced on the previous page. So this will give us an integration over r, and then in spherical coordinates we have a factor r squared. And this integral over r ranges from 0 up to the radius of the half sphere, which is velocity of light times delta t. Then we have an integral over theta. In spherical coordinates, we always have in the volume element a factor sine theta, and the integral ranges from 0 to pi over 2. And then we have an integral over phi, but we have axial symmetry. The fraction of photons emitted doesn't depend on phi. We have axial symmetry. So this integral over phi just gives us a factor 2 pi. So this is the integral over the entire half sphere that's kinematically allowed of the fraction of photons emitted. If we want to now obtain the fraction of the photons emitted from this entire half sphere, we should divide all of this by the volume of the half sphere. The volume of the half sphere is 1/2 the volume of an entire sphere, so that's 4 over 3 pi radius of the half of the sphere cubed. So this is now finally the complete formula to obtain the fraction of photons emitted within this half sphere. You see in the integrand that the r squared cancels, and this makes the integration rather simple. What you find is that this equals 3 times the area of the hole divided by 8 pi and then c times delta t squared. Now this is the fraction of the photons emitted from this half sphere. But what we are really interested in is the energy emitted. So from here we should somehow calculate the associated energy that is emitted. Now in order to calculate that, how do we obtain that? We can look at the total energy of all the photons inside the half sphere and multiply this by the fraction of photons that is emitted. When we do that, then we get the energy emitted. Yeah, we look at the total energy in the half sphere. We know a certain fraction of photons is emitted in time delta t. These photons carry with them the same fraction of the energy that was inside this half sphere. Now, the fraction of photons emitted, this is precisely the formula that we had obtained on the previous line. This is the 3a divided by 8 pi c times delta t squared. And what is the energy of the photons inside the half sphere? Again, we can split this up into factors. We can ask, what is the energy density of a photon gas? And we can multiply that, the energy density, we can multiply that with the volume of the half sphere. The volume of the half sphere, as before, that's 1/2 4/3 pi c times delta t cubed. And then what's missing still is the energy of density of a photon gas. But this is pretty easy. We have a formula for the internal energy of a photon gas. Let's look at that page where we calculated the internal energy, first line, internal energy of a photon gas. The energy density is simply this internal energy, U, divided by V. So we can take the formula from the first line, divide by V. This gives us the energy density. And I copy it here. When we multiply all these factors, then we find the final result. This is pi squared over 60, Boltzmann constant to the power 4 over h bar cubed c squared times temperature to the power 4 times area of the hole times delta T. The prefactor in front of the temperature to the power 4 is denoted as sigma and is called Stefan's constant. It has a value approximately 5.67 times 10 to the minus 8 watts per square meter and Kelvin to the power 4. It's a nice sequence of numbers, 5.67 10 to the minus 8, so 5, 6, 7, 8. Maybe that helps to remember. And then finally, you consider a quantity, a physical quantity called the emittance, denoted by R. That is the energy emitted by a black body per area of the hole and per unit time. So that's a quantity that's characteristic of a black body, that if you pinch a little hole inside the wall and you look at the radiation energy coming out, then of course the radiation energy coming out depends on the size of the hole that you pinched in the wall. So the energy per area and per unit time, that's characteristic for the black body, that's called the emittance. And with the result that we found above, this is equal to Stefan's constant sigma times temperature to the power 4. And this is known as the Stefan-Boltzmann law, which is the title of this page, that the emittance of a black body is proportional with Stefan's constant times temperature to the power 4.